see where this takes us. Perfect. Okay, welcome everyone to the 2133 midterm crash course. I was just saying before, this is going to be a bit more of an unorthodox one. Haven't had the bandwidth to fully prepare my own questions, so we're going to be having a look at some on-run resources and possibly stepping through some questions that other people have developed, and hopefully they might give you a sort of new insight into analysing 2133. Questions. So I guess we'll start off with some, let me just start with, so I've got our BJTs and we've essentially got something called the hybrid pi model for the BJT. So our hybrid pi model is what we use for a lot of our analysis methods. This is sort of an incomplete one because we don't have our capacitances. I might be able to grab up the entire, essentially we do have a capacitance up here and then also a resistance as well, and then a capacitance between base and emitter. But these are definitely equations that you should be committing to memory. So they're GM equals IC on VT. VT is 26 millivolts. It's thermal temperature. That can change at different temperatures, but we normally stick with 26 millivolts. So if you do 1 on 26, it's more or less 40 times IC. This is essentially called our Trans-Conductance Gain. Another really important parameter that we look at with our transistors is R pi. So R pi is our input resistance. Essentially, it's beta on GM. Beta is also called HFE. That's another important thing to remember. And I guess that gives us an expression for beta in terms of GM and R pi, which is another really important one that you should be remembering in case you need to convert between them. HFE we can find from our transistor or our transistor data sheets if we're in labs, those sorts of things, or it'll most likely be given. But you can see that actually beta is a function of GM, which is a function of IC. So if IC changes, our collector current changes, we're going to actually have a different gain in our transistor. Another important value that we're going to be interested in is our output resistance R0. VA plus VCE on IC, approximately VA on IC. But when we start looking at some of our graphs, we'll notice the effects that this extra term has. Some notes, these parameters are determined by the quiescent point or the Q point. Essentially, that's our operating point, and it's going to change the values of these based on our IC values, etc. This model will hold for both NPN and PNP devices. So no matter what circuit you get given, most of the time we get given NPN, but you might get a PNP, and it's exactly the same analysis here. As for symbols, you can tell these two apart by just the direction of the arrow. So if it's coming out, that's an NPN. And if it's going into the, whatever that is, the horizontal line, sorry, that shouldn't be an arrow down there. We've got a PNP BJT. So there are a few important things that we need to know how to use. I'll come up. Yeah, so this is our BJT basics, basics. So we have three different regions. One of them's saturation, one of them's active or forward active, and then one of them's cutoff. In our active region, we have the equation IC equals beta IB. This is essentially where IC only depends on IB and is not a function of VCE at all. So you can see even as VCE is changing, our collector current stays the same, and it depends on the different values of IB that we have along here for our BJT. Our Q point is essentially the biasing point that we're doing our analysis about. So you might see pictures where you get sort of a wiggle on the IC translated into a wiggle on the VCE. Essentially, that wiggle happens about the Q point. And if we have this linear relation where IC just depends on IB, we're essentially going to be acting like an amplifier, a current amplifier. This is what I was mentioning before with R0. So 1 on R0 gives us the slope, and you can see this is called our early voltage. So you might get, I guess, asked about what does the early voltage affect. Essentially, this is not a perfect straight line. So we are going to have some sort of slanting in our responses for our BJTs. These are just some important things to remember when we're thinking about the graphs. In the cutoff region, we're not going to have any. Essentially, our collector current will be 0 below this point, and in our saturation region, our collector current is going to be constant. It's essentially we've maxed out our base current to the point, or our collector emitter voltage is so low that we just have the same current no matter what. So we like to be in the forward active region because that's where we get our nice linear characteristics. And so hybrid pi is essentially when we're in our linear region. So we can replace our transistors by this only if we're in the linear region. And use the equation IC is beta HB IB. Actually, hybrid pi, I'm pretty sure it holds all the time. Okay. Another thing you might see on some equations, so not equations, circuits. This is going to be sort of the V circuit that we're looking at. So does anyone know what, let's have a look at the chat. Does anyone know what sort of, I guess, circuit we have here? So the term that we use is common something. Is there any ideas? Just try and find a nice way to do this. Common emitter. Thank you so much, Maya. Yeah, so we have our emitter connected to ground, and our signal is on the collector. So this is a common emitter circuit. And this is going to come up, this is sort of like the classic example of a BJT circuit. We're going to look at it for DC biasing. We're going to look at it for AC analysis. So when you see these capacitors here, the ones on the input and on the output are called coupling capacitors. And essentially they remove the DC. So the DC hits this capacitor and gets blocked from our input signal, and we just get AC differences. And then the reason we do that is so we don't affect the biasing point. Because you can imagine if our biasing point suddenly pulls us into, say, cutoff or saturation region, then we're not going to be seeing the correct output that we're interested in. And the same goes for this capacitor. So our biasing point won't affect our output voltage. C3 essentially removes the emitter resistance for quiescent point stability. So that's again for biasing reasons. And we choose that to provide a short circuit at sort of the low frequency. So we're going to get into our frequency response, but we want a short circuit occurring sort of on the lower frequency side. This is an equation for that if you're interested. And I'm going to copy this link and send it in to you guys so you can have a look at some of the resources that I'm using here. I highly recommend checking out some of these because they'll be super useful. Where to next? Yeah, I guess so we can think about our DC and AC equivalent. So if we've got this circuit, our common emitter circuit, for DC, all of our capacitors become open circuits. So we can essentially disconnect it there and disconnect it there. And this becomes our sort of DC biasing circuit. Let me just check to see. No worries, Anya. You don't think it works? Oh, yeah, my bad. Let me try and get it working. Weird. Where was I? Okay. Will definitely work. Yeah, so here we get a really good overview of our different frequency responses. And this is also going to be what we're using for our frequency response of the emitter follower. So I guess get keen for that one. Where was I? Yeah, so the DC equivalent. So once we've disconnected our capacitors, the next step that we take is to short circuit inductors. We want to have a look at VB, and then if you think it's forward biased, set VBE equal to 0.7. We assume we're in the forward active region, so we assume when we have a look that we're sitting somewhere in this range where we've got this nice relationship between collector current and base current. And then we find the different voltages around our transistor, so collector and emitter voltages, and then we make sure that our assumption of forward active actually makes sense. So we check that VBE is greater than 0.7 and VBC is less than 0.5. These are good values to keep in mind. So this is sort of a forward biased voltage, and then we want this to be reverse biased. Just give me 2 seconds. So sorry. In the meantime, definitely check out that article, and you might be able to start reading ahead. So sorry, I'm back. Where was I? So yeah, this is what the steps that we're going to take for DC biasing. DC biasing can actually be quite complicated because there's a few different ways that we can look at it. But essentially, once we've disconnected opened our caps, shorted our inductors, we get this circuit. And this is the circuit that we're going to use to calculate our DC biasing. There are actually, where did I draw them? Yeah. So there are, I guess, 4 different ways that we can DC bias our BJTs. I'm just going to open this link because I thought this was a very good, not opening. Thought this was a very good resource for looking at DC biasing. I apologize, it's running slow. Send that into you guys. So essentially, the first way that we can DC bias is by connecting our base directly to the VCC through a base resistor. This might also look like, this is probably one that you saw in lectures, just like a sort of a DC source. It might even have been shown as a battery, like this. And then your R base, and then that hooks straight up into your base. And then that might be grounded, there might be a resistor there, etc., etc. And then this goes up to your VCC. This could be anything. This could be VCC, it could be less, it could be more. These are probably one of the more simple ones to analyze because you can sort of assume this to be 0.7 volts and then just calculate that current, IB. The next way that we might see our transistor biased is with a feedback resistor from the collector. So you can sort of see the difference between this one. This one's coming from VCC directly to the base. The next one, we're not actually coming straight from VCC. We're coming from the collector of our transistor, and then we come through our base resistor into the BJT. Again, this one's fairly reasonable to analyze, but we'll have a look in that resource at the different sort of methodologies that we're using. The third one that we might have is actually an emitter bias. So we could ground our base and then have our, this is not actually grounded, by the way. We're still putting our input signal here, but this is just the DC sort of circuit. We could actually have a minus VEE, so a negative rail. And what that's going to do is essentially, I guess, pull current through the transistor and switch it on that way. And then finally, we have the voltage divider, which I haven't drawn here, but is essentially this, right? The voltage divider can get quite complicated if we want to analyze it perfectly. So I'm going to open up this resource. We'll take a look at it. And so I'll send this one through to you guys as well, actually. When we're DC biasing here, you can see they've got the base emitter loop. They've got a collector emitter as well. And then if we scroll down to the voltage divider, this is good because it's very stable. So you'll see this one a fair bit, essentially just resistors coming from VCC to our base and then from base to either ground or VEE. If we want to do it perfectly, what we essentially have to do is find our Thevenin equivalent of this circuit. Remember, this gets opened up, so we ignore this capacitor, that gets opened. And we also are going to open up the 50 microfarads. So if we're looking into, essentially looking this way, we can replace this these two resistors with a parallel combination. So R Thevenin is the parallel combination. And then E Thevenin is just, well, he calls it E, he or she, but it could be V Thevenin as well. And then this essentially is biased in the same, it's just like the first one that we saw, right? Where we have a voltage source into our base. And then we can obviously calculate the base current. One thing to keep in mind is you can actually reflect this resistance up into the base here. The way that you do that is with a factor of beta plus 1. So if I've got the my transistor like this with RE here and then RB, looking into this resistor, into this transistor, I actually see RB and then beta plus 1 times RE. And then I hit my transistor and I can ground that. So then this can be used in calculating IB. That could be really handy. It actually does sometimes play a role, like reflecting your emitter resistance into the base using this beta plus 1. So I definitely would add that to my sort of arsenal. And then we're assuming that we're in forward active, so we can use IC as beta IB, and then we calculate a value for IC. And finally, oh, I apologize, I've lost this. Finally, we can find a value for VCE that we're biasing at. Approximately, we can pretty much just do a voltage divider on this VB. And then assuming that beta RE is bigger than 10 times R2, we can just say that the current through here is just this voltage on that. That's always true. And then voltage at the emitter is, yeah, and then this voltage is that minus this drop. So it gives us an easier way to approximate where we just find this base voltage as a voltage divider, assuming that pretty much there's going to be very small current. Like IB is very, very small compared to the current that actually runs down into here to bias this point. They talk a bit about saturation. I wouldn't worry too much about that. The main thing is just being able to identify how your circuit is biased, and then what that means for your actual operating region, and possibly understanding where you sit on this graph, wherever it is. Where you sit on this graph, where is your Q point with regards to VCE, IC? Cool, were there any questions there? Just gonna have a bit of a drink. Nope, cool. Wonderful. Okay, so we've had a look at our DC equivalent circuit. AC equivalent, same sort of thing, but we're short circuiting our capacitors and we're grounding our DC DC supply. So we're essentially flipping it on its head. In this one, we're not so much interested in obviously operating points. We're interested in the behavior of our transistor to an AC signal. So we're going to be using our hybrid pi model in this AC equivalent. You can see we've grounded our DC. We've short circuited all of our capacitors. A lot of the time, if you've got a bypass capacitor, that's essentially going to bypass RE. So we can see that it'll make our analysis a whole lot easier. So if we have a look at our hybrid pi, essentially if we had a resistor down here, RE to ground, then we can't get rid of this node. Whereas if RE gets shorted to ground, we essentially can ground both of them and we don't have this annoying wire in the way. But you can do analysis with both. It doesn't really affect it. So let's have a look at our common emitter circuit. So I'll just quickly draw that back up in case you've forgotten. So we've got R1, this is our VI going in, and then we're going to have RB. I've actually forgotten how this was set up. I'll just wing it, I guess. Let's say that we're just grounded at the bring that down a bit. We're just grounded at the emitter. Bring this down. And then we had our collector, that was VCC. And then call this R3, and that was V0 over R3. So we're going to ground VCC. let's get rid of that and turn it into a ground. And so R1. Then we're going to replace our transistor with its equivalent model. That looks like R pi. Sorry, I think this RB was connected to ground. Yeah, so this was biased to the to VCC. Yeah, that's how it would have been biased. And then we have our GM V pi, and then R0 as well. Sorry, this is so messy. And they all get connected up to ground. Then if we take this, neaten it up, we get to this circuit. So looking at gain for this circuit, it's fairly reasonable. So the differential gain is going to be V out divided by V in. Best way to do it, V out on VB, because we get a VB here, and then VB on V in. If you have a bunch of things, like if you've got a few, transistors cascaded, then you do this on the first VB times VB on the second VB, etc., all the way through until you had essentially VO on the top and then VO on the bottom. So if we have a look at this simplified common emitter circuit for AC analysis, what we get is that V0 on VB is just by Ohm's law minus GM times this RL. And then VB on VI is just a voltage divider of sort of this parallel combination divided by that parallel combo plus that. We're going to say that this is approximately equal to 1 just for simplicity. And then our load resistance, R0 is a really big value. So you can remember here, this is really flat, right? So essentially that means that R0 is really big. Where were we? And then R3 is also much bigger than RC, just by design. So then we get that our gain becomes minus GMRC. This should be really familiar to you. So this should also be sort of committed to memory, I guess. Just say like AV is minus GMRC for this circuit, which is again minus 40 times IC times RC. Typically, we'd set this to be VCC on 3. So then our gain should be approximately minus 10 times VCC. That's just sort of a ballpark figure. Yeah, so I guess let's have a look at some AC analysis. So they ask us to calculate the voltage gain, input resistance, and maximum input signal level for a classic common emitter. We get given that beta is 100, VA is 75, and then we also know the operating point. This would be ICQ, and this would be VCEQ. We're assuming that it's in the active region. We also want to assume that the signals are low enough to be considered small signals. So the whole point of this AC analysis is that we're doing something called small signal analysis. And the reason we've got this emphasis on the small signal is because we're using a Taylor series expansion, which is where we essentially expand out the exponentials of our currents and then just take the first terms from them and the derivatives. That's it. So we're turning exponentials into straight lines. And so that's only going to be true in a small region around our operating point. So if you've done any maths to do with Taylor series and sort of truncating Taylor series, essentially our Q point is just the point that we're choosing to take our Taylor series about. So we don't want to go have our signals sort of changing too far out of that, because then the model that we're using is not going to align with how it's actually behaving. So let's have a look at this. Just this example and work our way through it. Cool. So the first thing that we do is we're going to calculate GM. So 40 IC, this is just IC on 26 millivolts. We get GM to be, this is our IC that we're plugging in, by the way. We get GM to be 9.8 millisiemens. Does anyone know what Siemens is the unit for? Or can you figure it out? How it is? So you might almost also see it written as ohms to the -1. It's a transconductance or a conductance value. So GM is IC on VT. Remember, ohms of volt V on I. So GM is going to be ohms to the -1 or Siemens. Good sanity check there to see if you're getting the right values. We calculate R naught using this big equation, VA plus VC on IC. We get a huge value, right? That's what we're normally assuming. R naught is really big. Our load resistance is going to be those three in parallel. I'll take it back up to here. You can see it's those three in parallel. We're using that same setup, which is 17.1 kilo ohms. R pi is beta on GM. We've calculated GM. We've given beta of 100, 10.2 kilo ohms. Again, this is dependent on our operating point because GM is. And then RB is that weird Thevenin thing where we've taken the these two in parallel. And then finally, we can find the parallel combination of RB and R pi, just like in this. We're going to lump these two together. To find AV, we can pretty much just say that it's minus GM times RL, right? Because this value is, if we look at RB, R pi versus R1, 160K, that's huge compared to it. Oh, I beg your pardon. Yeah, that did seem right. Compared to 1K, it's like a factor of 10, right? So it's 9.2 on 1 plus 9.2. So it's 0.9. Better to calculate it in, but there is not, significant difference. Our input voltage, if we come back up to our equivalent circuit, essentially what we're seeing here is just R1 plus that parallel combination. You can see we get Ri plus that parallel combination. We get a certain resistance. You'll often be asked to calculate the input resistance. So it's good to understand the different ways that you might see it. And then to find VBE is just the voltage across our R pi. It's just a voltage divider. So giving us a range for VBE of 5 millivolts, I think it was. Maximum input signal level. I'd have to check why that can only be 5 millivolts. I think they've just chosen this value. So we want to stay within our linear operating range. So we choose a a 5 millivolt sort of change in VBE. And then that translates to a, yeah, a 5.54 millivolt change in our input. We can check if our gain is in the ballpark. So remember, it was -10 times 12, which is -120. The gain that we actually calculated was -150, which is roughly what we think. And then if we know what our input sort of range should be, to find an output range, all we have to do is multiply that input by the gain. This is change in VI, and this is our differential gain. And then we can get a sort of output swing. So if we have some little output, put it through a gain, that's the maximum output, was 0.8 volts. Was there any questions about the finding the gain AC analysis? Any queries or questions, or want me to go back over anything? I'll copy this one into the chat as well. Nah, no stress. Okie doke. So that's halfway through. You might leave it there for 5 minutes, just take a quick 5-minute break. And then we'll come back and have a look at some frequency analysis and some of the resources that I found around that. Yeah, get up, stretch, get some energy. We'll see you back at 1:50. Okie doke. So, welcome back. Hopefully it was nice to have a bit of a break, a bit of a stretch, a bit of a relax. We might start having a look at frequency analysis because I know this is a biggie and can be quite, I guess, confronting analysis. I'm not going to say that I'm perfect at it either. It's definitely a lot of redrawing and getting things looking neat, and there are a few little hacks here and there, mostly to find the Thevenin resistances. And I guess the main one that I think of, which I'm going to keep coming back to, is am I here? Might be even here. That when we're reflecting resistances between base and emitter, we can use this factor of beta plus 1. So it gets multiplied by beta plus 1 into the base, or you can divide the base by beta plus 1 to get it into the emitter, and that works just as well. So let's have a look at frequency analysis. I'm going to this. How's this working for everyone? Do you like this style? Zong, yeah. Okay, that's good. Excellent. Alrighty, so frequency response of a BJT is pretty much determined by the different capacitances that we have in our BJT. So we have a low frequency band where it essentially tails off, a mid frequency band, which is where we get sort of a constant gain throughout the frequencies, and then the high frequency, high frequency band where it starts to tail off again or attenuate. This one is because of our bypass and coupling caps. So we're sort of determining that. They become sort of short circuits, so we don't really worry about them. And then at this high frequency, these are sort of semi-large, right? They're large capacitances. Here we have the capacitance is sort of internal due to, essentially we have in our BJT, we have N, then P, then N. If we have a voltage difference across this, and then we have another voltage difference here, all we need is a charge divided by, sorry, C is equal to Q. It's one of them. I have to remember. All we need is a charge and a voltage. And if we have charges and voltages, we're going to get capacitances occurring. So there's no capacitance between our collector and our emitter. There's only one between base and emitter, and base and base and collector, and base and emitter. This one we call C mu, this one we call C pi. So they're what's affecting this high frequency band. So low frequency band, we're going to need to start with our, just keep moving, not hybrid. We like hybrid pi. So hybrid pi, we've got C pi, C mu, R mu, all of these resistances playing into it. The transition frequency essentially governs the highest frequency that we can operate well, that we can assume this hybrid pi model is holding true. So if we have our frequency less than or equal to a third of this transition frequency, then hybrid pi is good, is working. So they've quoted it here as beta on 2 pi r pi c mu plus c pi. Beta on r pi is GM. So we could also have GM on 2 pi. On 2 pi c mu plus c pi. And that's essentially going to govern the frequencies that we can consider this model to be good. Here are some calculations if you're interested in those. I'm pretty sure I sent this into the chat, right? Yeah. Excellent. So let's have a look at some analysis of a common emitter at high frequencies. We're given a quiescent point. We assume it's room temperature. You can calculate all of these values if you're interested. Oh, these we get given. And what we're going to do is convert this into its equivalent, first of all, AC circuit, and then we get the hybrid pi in as well. So RS is going to sit at the source. We get this becomes a short at high frequencies. This is high frequencies, yeah. Our RB becomes connected to ground, same as the rest. These both get grounded. Short circuit CE will counteract RE. If that wasn't a short circuit, RE would be sitting here. And what we're going to do is we're going to do a, we'll think about using our beta plus 1 if we have to calculate equivalent capacitance, resistances, etc. But moving forward, we're going to run into a bit of trouble from something called the Miller effect. So what capacitance is causing the Miller effect here? Out of these two capacitances, any ideas which one is causing the Miller's effect? Okay, no ideas. So essentially, Miller's effect is when we have a gain and then a sort of an impedance between our input and our output. I'll just sort of draw how I was shown Miller's theorem. Essentially, if you have some sort of V1 and then an impedance and then V2, and that's V1 there, that's V2 there, and this is ground. And let's say that there's some gain which is V2 on V1. What we can do is we can actually turn this is exactly equivalent to if we have V1 across an equivalent load, which has been scaled down by 1 minus K, and V2 across an equivalent load, it's been scaled by K on K minus 1, plus or minus V2. So we're starting with sort of an impedance across two voltages, and there's a gain, and it's very important that this K is less than 0. So remember, for a lot of these, we've been working with essentially the gain was minus GM RC or RL. So that minus means that we can actually apply Miller's theorem to this C mu. So that's exactly what we're planning to do. We're going to essentially break it up into two new impedances. One of them is going to have a value of 1 Z on 1 minus K. One of them is going to be Z times by this different scaling factor. If you're interested in derivations, just Google them. I'm sure they'll come out. But essentially, we can also do the same for R mu as well, right? And C mu. So if we want to find the R mu on the output, we can multiply it by K on K minus 1. Remember, that's this one here, K on K minus 1. AV is essentially just our minus GM RL dash. That's exactly what we've seen before, right? It's this one for this one. This is minus GM V pi. That's V pi. And that current flows up through all three of these resistors and down through here. So that current has a value of minus GM V pi. So then this is our output voltage. We can also find the input resistance due to Miller's effect. And it's going to be divided by our 1 minus K factor, which becomes 1 plus GM. Finally, we can find the actual gain. AVS is V0 over VS, taking into account these Miller effect resistances. So this is Miller's effect plays a role not even just in high frequency. It actually plays a role in the midband gain as well. So you can see that the AV that we were calculating without considering R mu was minus 97. As soon as we start to take into account these sort of large resistances and changes to our values, our gain comes out as minus 86. There's been quite a dramatic decrease in our midband gain even from the Miller's effect. So Miller's effect is sort of something that we don't really want to have. It's not good for our frequency response. We'll have a look at a few ways that we can minimize that. I'm just having a look to see if these all seem very complicated. You can see obviously these become very complex very quickly. Follower. So we might be able to have a look at this one. More Miller's effect calculations. That's exactly what we want to see. 1 plus that. Okay. So when we start looking at the actual high frequency analysis, we're going to use a method called the open circuit time constant method. So we essentially draw our AC equivalent, draw our hybrid pi, include that in it, and then we open circuit all our other capacitors and have a look. I'll see if I've got a frequency analysis question. Hopefully I've got something I can work with. These are sort of generalized expressions. Let's just have a look at this. So a lot of these have been derived a lot, right? We have a very, I guess this is a common configuration. So it's always good to just check out some of the literature that's out there. If it doesn't look like anything that you've seen, it's probably not worth trying to force your brain to understand it. But sometimes there's some really good content that might just there's a simulation if you wanted to see a simulation. Yeah, some of the online resources are good and some are not as good. So I guess the main thing to remember is Miller's effect, knowing those formulas, knowing the gain that we're going to be using for those formulas. So this K value. Knowing this K value is really important, and knowing that it has to be negative. I mean, I guess we could have a look at a pretty simple high frequency circuit, and then go from there. Yeah, let's do that. Yeah, so again, you're going to see this common emitter amplifier showing off time after time. Again, it's our classic hybrid pi. This should be committed to memory, so you should know that this is our base, this is our collector, this is our emitter. Got this nasty C mu sitting in the middle. And we're going to have to use our Thevenin resistance for the open circuit time constant. So let's have a look at C pi first of all. So we want to, again, it's called the open circuit time constant method. So we're going to open circuit C mu, that's good for us. Gets opened up. And then we're going to find the Thevenin resistance that C pi would see when we've grounded our source. Now this is quite simple, right? We can see that it's just R pi in parallel with RS. So then the open circuit time constant is just going to be this resistance times the capacitance, C pi, and we're halfway there. Now what we can do is we have C mu, and we're going to open circuit C pi. This one might be a bit more complicated, but we're essentially looking for the Thevenin resistance that C mu would see. We attach a test source because we've got this dependent source, remember? this current splits off into two different currents. One of those currents is the voltage at this point, which is this voltage plus this voltage, divided by this resistance, and then the other is GMV pi. And then we can also say that IT flows in the negative direction through there, which is V pi on that. We want to get rid of V pi in this situation, so we've just got a value in terms of VT and IT. That should give us an equivalent resistance, RT, for the mu. This is our Thevenin resistance. And so our open circuit time constant is just going to be, again, this resistance that C mu would see times C mu itself. Finally, we take the sum of them. This is what the open circuit time constant method is asking us to do. We take the sum. And then, I'm not sure what they're doing in this step. Possibly expand. Oh, they just expanded these Thevenins. And then for one pole being much, much bigger than the other, apologies for that. For one pole being much, much bigger than the other, we can approximate the sum of the poles with one of them. If they're not much bigger than the other, then we have to use a factor of 1.15. And essentially, this is omega high or upper. It's going to be the point in our frequency domain that sits here. Upper or high. And yeah, it's just equal to these values. We can have a look at a different model where we have to use Miller's effect. Common collector, common base might be interesting because we don't get. Yeah, okay, this is a really good one. So I might just screenshot this and send it in to you guys. This is a very good summary of the frequency responses. So some circuits will suffer from Miller's effect and some will not. So being able to determine which ones will suffer and which ones will not is a very important skill. So how do we get no Miller's effect? There are a few ways. So as we see here, we get Miller's effect when we're using our classic common emitter or common source for MOSFETs. So common emitter inherently has a capacitance between the base and the collector, the C mu. If we use something called common base, we're essentially applying just ground to our base. And then we apply our input signal, the in, to the emitter. And then output from the collector. That's one method. And the reason is because there's no capacitance between here and here, right? That's not a thing. The only capacitances lie between base and emitter and base and collector. We can also sort of combine transistors. So if we use something called Cascode, we've got a load resistance coming into a BJT. And then into another BJT. And this is RE. And then our input VS is here. Imagine we've got some biasing happening, right? That's just our classic voltage divider biasing. Don't need to worry too much about the technicalities there. Just assume they're doing their job. And essentially, the Miller's effect will be minimized because the resistance RE at this emitter is going to be R pi on 1 plus beta. So that's again this sort of reflection term. So if it's R pi divided by 1 plus beta, then Miller's effect, if you remember, is for any Z. So it's also for the resistance. So if we can bring the resistance, so decrease resistance, will reduce the effect, Miller's effect. We can also sort of cascade them like common collector into common base, or common collector into common emitter. Those are two other options that we can think about for reducing our Miller's effect. Was there any questions about that? We might have a look at a low frequency analysis too, the short circuit time constant method. Let's see if any of these are any good. Okay, that does not look very helpful. Sometimes the best way to learn is to see a whole lot of different ways of doing the same thing. So I would recommend looking at a common emitter circuit, because at least we're fairly familiar with that one. And then if there's one part of it that you're not sure about, just open a lot of these sort of other resources out there and the textbook as well, and just see if will help you in some way to understand. So this is talking about coupling, and yeah, okay. So it looks pretty good. So we've got our generalized method, right? So before we were using the open circuit time constant method. Obviously, there's a difference here. We're doing 1 divided by. For high frequency, we were doing 1 on omega high is equal to the sum of RC. So a bit of a difference there. Just always refer back to these equations. Don't try and commit them to memory, if that makes sense, because there's a 50-50 you'll just get it wrong, and it's not worth getting it wrong, especially in like an assignment or something. So we're going to have 3 capacitances at low frequency, right? So our high frequency effects aren't coming into play from this transistor. We've just got C1, 2, and C3, our coupling capacitors and our bypass. So we're going to have to. They're doing this an interesting way. We're gonna try and understand this as best we can. They haven't gone to hybrid pi. They're just keeping the transistor as it is. So let's do our best. So let's see where they're starting. So this is our short circuit method. So I don't know where R1 is. Maybe they've done that one. Here we're looking at R2. So we open up R2, short circuit the rest of them. It's nice because our bypass brings it to ground. R4 gets bypassed. This becomes a short, and obviously we ground our input. Yeah, they're doing some funky reflection stuff. So we're going to try and dive into this so then we're understanding it a bit better. Okay, so here's R1. Let's start with R1. The resistance that R1 of S is going to see is going to be, essentially this goes to, R pi goes to ground. So it's just going to be this one in series with those two in parallel, RB and R pi. Not too bad there. So we're happy with R1S. R2S, similar deal. So we're going to have our R3 in series with RC plus R0. So we're going to hit R0 here. And then it goes to ground, so we don't have to worry about these two. R3 is going to get a bit funky. So R3 is sitting down here, and we're looking for the resistance into our third capacitor. So it's going to be R4 in parallel with sort of this resistance reflected into our emitter. So this resistance here is, there's R pi connected between emitter and base there. I'll just neaten this up. So we've got this point goes to a resistor R pi, and then it hooks up in there. So let's combine these two, call it R Thevenin, RTH. And then let's add that to R pi. So we just have one resistor and then our BJT. Now, do you remember that hack that said we can actually bring this into here by dividing by beta plus 1? We're going to use that here. You can see that it's R4 is going to be in parallel, and this goes to ground, with the reflected resistance here. So if we, I'm just going to neaten all of this up. If we take, sorry about that, this resistance and R pi, which is hooked up through our transistor, we can actually turn it into a parallel resistance with a value of R total divided by beta plus 1. So that's exactly what we've done here. And then we can just sort of sub in those different values. So that can be a really handy thing for these annoying bypass capacitors on the emitter. Essentially, those are the ones that look like this, R pi, and then you have RE, and then you have your GM. So you have your GM R pi down here. GMV pi, sorry. So if we're looking into these terminals here, this gets sort of reflected down into a parallel resistance divided by beta. It might save you a bit of time. So then now that we've got all of these values, we've got our 3 resistances, we've got our 3 capacitances, we can get an estimate for the lower cutoff frequency. Here they found it to be 735 Hertz, and they've noted that R3 on C3 is going to dominate. Essentially, that's just so big, it doesn't really matter what these two are. And if we have a look back up here, R3 was this time constant was our bypass, and we essentially use it to set the lower frequency. These other two do have a bit of an effect, but that's not their main goal, right? They're coupling, they're blocking DC. The bypass capacitor is what we're using to set this lower frequency. We can do the exact same thing with the MOSFET. Maybe it might be worth having a look at a MOSFET for low cutoff frequency, just because you might get thrown it. I'll just double check I've sent this through. Send that. Hopefully that's working okay. Yep. So you'll have access to all these resources. So MOSFETs are even nicer because instead of an R-Pi, we just have, it's an open circuit. So we just hit this and get our VGS. And then we get a current source. So actually, let me just double check that. Yeah. And this is GM VGS. And we do still have an R0, but less of an issue. This is sort of our small signal model. And again, exactly the same things happening, but it'll be nicer because we don't have an R-Pi in here. So for C1, we jump in here, we're just going to have Ri plus that there, which is just that plus that in series. For C2, going to be RD, well, this R3 plus RD in parallel with R0. Remember, we've got our R0 still. We can't forget about that. Just see if I can make this. And then finally, C3, we've got, this is a bit of a wacky one, but essentially we get a, yeah, 1 on G. Weird. That's going to come out of the fact that we've got this is going to be VS. VG is going to go to 0, so this is only going to depend on VS. And then we've got our RS here. And then we want the resistance in looking into these terminals. Yeah, I'd have to think about why that is coming out that way. If you have any ideas, please shoot them through. GMV. That point there is VS. Yeah, so looking into this terminal, the resistance that we see is VS divided by IS. Obviously that is IS there. So then if this VS, this is essentially VS divided by GM-VS, which is just 1 on GM. So essentially this is really weird, but a really important point. Oh, sorry, I went too quick. When we're looking into the source of this MOSFET, our gate is connected to ground, right? So we can consider this ground. So VG is equal to 0. I might have gone too quickly there. VG is equal to 0. If in our model we're using the fact that the current gain is GM VGS, if VG is equal to 0, this is the same as GM times VS. Now this point here in this circuit is VS. So that means we've got a current which depends on the voltage across it, or the voltage at a given point it's connected to. So this GM, this is actually going to act like a resistor with a resistance of 1 on GM. So remember, GM is a transconductance, so that's why we can say that R2S is actually RS in parallel with this sort of funky resistance. It's not really a resistance, but can be considered that way. Cool. Okay, hopefully that made sense for everyone. I can just save all of these and make sure that they're available. Thanks so much for coming, everyone who came online. And if you're watching the recording, yeah, thank you for watching. Best of luck with your take-home midterms and with the rest of analog electronics, and we'll see you again for a finals crash course pretty soon. Check out the ELSOC Academics YouTube, which is where this video is going to be put, and also our website, elsoc.net. There's some great resources. We're trying to start up a new wiki as well. So if you want to contribute to that, we'd much appreciate it as well. Cool. Alrighty, I'll leave it there.